So we're going to learn to find arc length for vectors in 3 space. You know, so 3 space, 4 space, 10 space, whatever. It's shorthand way of saying 3-dimensional space. You know, so we say 3 space instead. You know, and you become more comfortable with that if you have a little bit of experience with linear algebra, although it's not necessary. Arc length. Look at that formula. Very, very similar, if not identical, to what you've been accustomed to. It's essentially the distance formula, right? Distance formula involving derivatives, right? So it's the sum of the squares of the derivatives under the radical, right? So what we're doing here is we're finding distances on an instantaneous level, right? So I always equate it to the idea, I mean, I went to elementary school in the 80s, so like my examples can be dated sometimes, but when we were learning about map reading, we would have the map and then we'd have like a little legend at the bottom, the little key to interpret, you know, like this, where am I? This distance is 500 miles. And so what we would do is we take a little index card and we just kind of trace along the map, making little tick marks until we added up to that distance, and then we would have 500 miles, right? But we do it on such a minute level, teensy tiny little distances, and then we would aggregate those distances until we ended up getting to our desired distance, which was 500 miles, or whatever they designated as 500 miles, right? But we did it on a micro level, right? And then collected them all at the end. That's what an arc length formula does for us. That integration part takes all those minute little distances and then smushes them all together at the end. And then you have the arc length over an interval. Now, a fun little consequence of this is that also happens to be the same as the magnitude. You know, when you find a distance involving a vector quantity, you're in fact finding magnitudes. Now, if I tell you that f, g, and h make up the vector valued function r, then f prime, g prime, h prime will make up the vector valued function r prime. So finding the magnitude of r prime is essentially, you know, over an interval, integrating, is essentially the same idea as finding the arc length. So we need to compute the arc length for the curve traced out by the vector valued function of cosine plus sine plus t, right, ijk. This is what it looks like, kind of. It's just some kind of curve, but we know, we do have some experience with this. We actually graph this. This is more of an elongated version of it, but it's like a spiral staircase. If it continued on, it would look something like that. Over the interval of 0 to 2 pi is what we're interested in, right? So it's one of those things where it's like, just have at it, because I need, if I'm calling f of t, that's my cosine of t, I need f prime of t, which is negative sine of t. All right. Then g of t, my second component, is sine of t. G prime of t is cosine of t. And then in the last little bit there, h of t is just a t, which means h prime of t is 1. So a constant rate of change for the h of t vector value function, or the k component. But these are the crunchy bits and pieces here. So if I'm going to integrate this over the interval, we'll do it by hand and I'll show you on the calculator. 0 to 2 pi. The squared values, let me highlight. Squared, squared, and squared, each one of those. So shorthand, sine squared plus cosine squared plus 1. Right, that's all going into our model under a radical dt. All right, now, hopefully, you know, at least know enough of your trig relationships. That came out a little too snarky. But this is an important one. So if you don't know this one, make sure, for the love of everything, make sure you know this one. Sine squared plus cosine squared is equal to 1. So we're looking at, on the interval of 0 to 2 pi, the square root of 1 plus 1 dt, which is going to give us root 2 t on the interval of 0 to 2 pi, which in turn will give us 2 pi radical 2. Now, these are linear units. All right, they didn't give us any units on the problem, so we just say units. All right, so 2 pi radical 2, and that's really it. All right, so let me save this as integral VVF in 3D. I'm just saving that, so you know I'm saving that one so that next time I want to integrate the 3 different components, I just put them in as F, G, and H. But what I'm going to do, I don't like when that happens. It just crashed on me. I mean, I don't know anybody who would like it when that happens. But so I got that saved. I want to do something different with it here. So what I'm going to do is I can, I can just tweak this one. And I'll save it as something different later on. All right, so I got cosine cosine of x. Just want to make sure variables aren't going to matter here. So we're good. Sine of x. And then the last one would just be an x. All right. I just like to make sure that I'm working on a reasonable interval. So I'm going to change my window to go from 0 to 2 pi and make sure there's no funny business going on there. You know, and it looks like everything's good to go there. Yeah, I don't see anything too crazy. Yeah. So we start out at 0 to 2 pi and just kind of go from there. But that's good. All right. So no funny business. It's always a good thing. And so what I can do then at this point, really at any point, is integrate from 0 to 2 pi. Now this is a radical. So I'm doing, I always get nervous about parentheses, so I tend to overdo it to the point where it's like, man, you really overdid it on those parentheses. Like it becomes a noticeable thing. You know what? I'm going to try it without the parentheses first. Oh, that's not. Get out of here. Get out of here, kid. You bother me. All right, so there. Plus. All right, and so we get that, which may or may not be right. It doesn't look right. So I just want to make sure about the parentheses. Yeah, that doesn't seem to be making a difference. All right, well, so I got the answer that I was looking for there in that the parentheses don't make a difference. So that's good news. Oh, you know what? All right, I didn't put the derivatives in, but I wanted to, okay. I'm just curious about something here. I actually never tried it with the prime. No, I don't think primes work on this. I think I have to use derivative notation. That's all right. Survive. Oh no, it did work. Oh, that's good to know. All right, we got there. Anyway, just a quick double check Aruski here, make sure. And there we go. We got the same value. So honestly, I keep running into the issue of like my GeoGebra knowledge and my Desmos knowledge, the getting the two confused. So it's good to know. So yeah, I put in the functions f, g, and h, and then I put just a general idea or general formula related to the arc length. And so what you could do is, if you really want to get fancy, maybe you don't want to get too fancy, but what you could do is make this A and B, create those sliders so that you really have a general case where you could say, all right, all I have to do is change my F, G, and H depending on the nature of the problem. So you look at the next problem, it's like, I think we could probably just crank it out just with this, but I can manipulate my A to be 0 and my B to be 2 pi. And then I just go back up and it kind of retroactively computes my definite integral, right? So then this would be a save. You know what? I'm going to save it later because I want to save it. I want to save it as a new one. So I'm not going to overwrite the one I just did. But if you look at the second example, we now just kind of made our lives easier. This is 5 times the sine cubed, it is cubed, of x. It might not take that. Oh, well, that's weird. I don't like that either. So parentheses, when in doubt, parentheses. Same thing with the cosine. The 3 cosine, close it up, cube it. Don't need the ones in, well, whatever, it's fine. It's all gonna work. A little heavy-handed with the parentheses here. So I'm gonna trim it down, but it's fine. I got a space there that I don't need. And the last one is just a t, so we're good. Messy looking graph, definitely not a picture perfect looking graph, but my A and B values are 0 and 1 still. So spits out my area model and we're good to go. Now you're not looking at, arc length model. So we're not looking at anything more than just the computational component of it, right? So if you needed to come up with something a little bit more elaborate, like, show an analytic response, I would need at a minimum from you the integral that you use to get this answer. Now you might remember from Calc 2, I definitely did this. Sometimes the questions weren't, give me the volume. It was give me the integral that you would use in order to get the volume. People definitely like those questions a whole lot less than the simple ones of just give me the volume, because then you can just pop an answer down, take a wild guess on a multiple choice question, and that's it. But to get the learning across, to demonstrate your knowledge and skill, it is kind of necessary for you to show some work sometimes. So 15 sine 2t cosine of t, that quantity squared, that's the derivative of the first piece. I'll put it all under a radical afterwards, plus 9 cosine squared t times negative sine. So I'm going to make that, oh no, I still want to leave that there. but I'm going to flip it in front, sine t, that quantity squared, plus 1 squared, which is just a 1, pop the dt here, and then get my radical through in here. Poor quality radical. And there we go. All right, so this ends up being approximately 25.7 units. Now, in terms of the work, I don't feel too bad about glossing over this a little bit, because really it's the same structure as the previous one, just a little beefier. You know, you square, you factor out some GCFs, you clean it up a little bit and start working out. But, you know, you do have a reasonable expectation that I am going to ask you to come up with arc lengths, but also a reasonable expectation that a lot of those instances will be with the support of a calculator. So, and that's just because of the double dip. I don't like doing that. You know, you've already been assessed on your ability to integrate or not integrate. You're allowed to take this course, which means that you satisfied somebody's requirements for Calc 2. I don't need to then assess you on all that stuff again. You know, so we kind of move away from that a little bit. Especially when there's plenty of Calc 3 stuff to assess you on. I don't need to go looking for extra things. I'm just making that look a little nicer. All right. So number 3 is kind of an interesting problem. It says find the arc length for the curve formed by the intersection of the cylinders. And then that's all it gives you. So you look at that and say, whoa, that's a little intimidating, because it doesn't give you an R of t. What that's telling us is that we actually need to come up with the R of t. So let me get you going on this one, and then we'll see where we are time-wise afterwards. All right, so we have x squared plus y squared. X squared plus y squared equal to 9. So in 2-dimensional space, that would be a circle. But because we're in 3 dimensions, it's a circle with infinite height, which makes it a cylinder. All right. Then we have y squared plus z squared is equal to 1. All right. So that is a circle equation. Still has the same structure, but you can see the variables are y and z, which means that this is happening for all x. So this is a cylinder along the x-axis. I gave you the diagram there because the purpose behind this question isn't to test your ability to visualize the graphs. It's more so to do something with the information that you have. All right. But if we're going to come up with the intersection in 3 dimensions, then it needs to be in the form of parametrics, and that parametric is going to have 3 components. Right. So if you really look at it, I'll zoom in, do a little extreme close-up action here, like extreme close-up. So the intersection between these 2 surfaces is going to be a path that, you know, because perspective being what it is, the only one that I could actually identify is this one, but you got to imagine that there's the other piece of it behind, you know, and because I'm not even, like, it would be irresponsible to even call me a bad artist. That's how terrible I am. Right? But you got to imagine that there's another piece behind the scenes, and then you got the same thing going on the opposite side. It's just it's happening behind the scenes. So you'd have something going on over here, which I can kind of try to emphasize, but then also more going on behind the scenes. So it's the collection of all 4 of those pieces that we're looking for. So the front side of the circle on the left, the back side of the circle on the left, the front side of the circle on the right, and the back side of the circle on the right. You need all of that, right? That's going to give us what we're looking for, the arc length, right? Now, we can go about this a few different ways, but I think the easiest way would be first to come up with a model that represents the pathways, but also, since we're looking at something that's going to be symmetrical, we want to try to use that to our advantage. All right. So let's get into the idea of trying to come up with the parameters here. All right. So I need an x equals, a y equals, and a z equals. I have two equations with three variables, so one of them is going to be free. That's fine. What I can do is I can solve my first equation. I can solve that for x in terms of y. So x squared would be equal to 9 minus y squared. And do the same thing for the second one. Z squared would be equal to 1 minus y squared. And that would make, so x and y are in terms of z, x and z are in terms of y. So that would make y the free variable. That's kind of nice. Right? And there's a little bit more to it than that, because I need x equals, so I'd have to root both sides. Same thing for z. So that's leading me to really the same stuff, just with a whole lot of pluses and minuses. So x would be equal to plus or minus 9 minus y squared. Y would be equal to plus or minus 1 minus y squared. If I tried to somehow solve these equations for y, it would be in terms of another variable. So the best I could say, really, is that y, since it's a free variable, y is just equal to y. Y is equal to itself. Right? Now, for the sake of keeping things in a more organized fashion, what I'll do is just shimmy things around so that it's in alphabetical order. Well, you know what? Undo, because the arrows won't make any sense. I'll just copy paste. I missed the copy. There it is. And then I'll paste it over here. And then I'll shimmy them around. Shimmy, shimmy, shimmy. All right. Now, y could be anything. So when we say y is equal to y, that's all well and good. But since we're talking about parameters, and we also want to have it as a vector valued function, what we would do is let y equal some arbitrary variable. And since we have the choice of what it could be, why not let it be equal to t? Because that's ultimately what we're looking for anyway. So oops. So all my y's are going to get swapped out for t's. I'm going to resize in a sec. Get out of here. There we go. All right. So let me just snag this. I'll bring it over here. Bring this up a smidge. Bring that down right now. Organization. That's the key. Enjoy the view. So we have all this stuff going on. And so now I could define my vector valued function. So I would let r of t too thick now. Could be equal to. Now, the big question is, do I want to work with the plus or minus? Do I want to work with, just the plus, just the minus, both of them at the same time? The short answer is you don't want to work with too much. So let's just take the positive components. The idea being that if we could figure out the arc length for just the positive pieces, then that'll give us 1/4 of what we need. All right, because again, we have the circle on the front from the left side, on the back for the left side, front for the right side, back for the right side. All right, so if we have all that information in hand, then what we can get as a result is something that we're just a multiplier away from giving us the final answer. Right, so my R of T is going to be this model. So K, geez Louise, T and J, and plus 1 minus T squared, and then K. So I need to differentiate all this. Some parts easier than others. So I need my R primes. And then from there, I need to actually pop it into my arc length formula. But that's going to be the easy part because I'm going to do that on Desmos. All right, so R prime, I'll go get a fresh new color here. Let me go with this nice light blue here. So R prime of T, really 1/2 9 minus T squared to the -1/2 times the -2T. All right, so 1/2 9 minus T squared to the -1/2 times -2T. That's my I component. Well, it's not really I anymore. So you know what I'll do? I'll just call that F prime, so I don't have to worry about the notation too much. So F prime, G prime. I'm gonna get a red involved here. It's just a 1, and then purple. H prime, 1/2 1 minus T squared to the -1/2 times -2T. All right, so those are the derivative values that I would pop into the formula. I mean, there is a benefit to cleaning it. That jumped on me. To cleaning it up a smidge. So let me do that. Let me do the smidge cleaning here. Might be a little easier to type it into Desmos, if anything. So -T over that. That's where I'm running into trouble. 9 minus T squared. Desmos handles fractions very nicely, so I'm not worried about that. -T over 1 minus T squared. All right, so we have everything but the bounds. You start thinking about it, it's like, okay, well, what could my bounds be? Well, it's got to be in terms of these circular values, and based on the fact that one of them is a 9 minus T squared and the other is 1 minus T squared, it's like, is it circular? Is it elliptical? That's kind of beyond the point. We just need a domain for my vector value function that's going to make sense for all components of that vector value function, right? So I know that I got my formula, my nice looking formula up there, you know, the S equals all that jazz. But I need the A value and the B value in order to make the whole dang thing work. Right. So when I go to put this in, I mean, I could just write it in general terms. And, you know, there's something that I kind of actively encourage people to do is, oh, that's too thin. Oh, redo. So we would say S is equal to the integral. I need this guy and I need that guy, but I know everything else is good to go. F prime squared plus G prime squared plus H prime squared dt. And also, after all this work that you see here, you start to get to understand the idea behind like why I'm allowing things like the Desmos calculator. Look at all the work that you had to do in order to get to a point where you could actually be ready to put it into the calculator. Right. So that's kind of the trade-off there. Where it's like, you know, the Calc 3 stuff is enough work, like I was saying before, not to beat a dead horse, but the Calc 3 stuff is enough without having to go out of my way looking for Calc 2 stuff to throw on top of it, right? So I need that domain. So I look at the different components here, and I see a 9 minus t squared, and I see a 1 minus t squared under a radical, right? So the domains would have to be such that we have positives under either radical. Well, we have a more restrictive radical for the second piece, or the second radical, that is. So I'm going to grab that one. I'm going to pull it off on the side here. And I'm going to say, all right, I know that 1 minus t squared has to be greater than or equal to 0. All right. I'm going to subtract the 1. I'm going to divide by -1. So we're looking at t squared has to be less than or equal to a +1. All right. Which means, you know, if you kind of extend the process, t, the absolute value of t, that is, has to be less than or equal to 1, which means that t has to be in between -1 and 1. All right. So that's my domain. If I did the same thing for the 9 minus t squared, I'd get -3 to 3. So it's the same computations, or at least the same process. The thing is, I get values that would work for the 9 minus t squared that I know would be outside the domain for 1 minus t squared under the radical. So, you know, there's no point in looking at the other one because it's just going to give me some values. Yeah, it would work for the 9 minus t squared, but it's not going to work for the other one. If it works for 1 minus t squared, it's going to work for the 9 minus t squared. So anything between -1 and 1, if I pop that into the other radical, it's going to be perfectly fine. All right. So you look at this and say, okay, well, how do I know? How do I know this is going to give me the right part of the graph that I'm concerned with? Well, that's where your GeoGebra calculator comes into play. Like hopping back and forth from one calculator to another, it's enough to drive you insane. But it's something that you want to get to a point where you're capable of navigating. I'll go back to that in a second, but what I want to do is just kind of hop you along to the GeoGebra calculator, pop this information in, and show you what the picture looks like so that we can kind of continue on this journey. Now, we would go to the original vector value function here. So you could use the radical tool, or you could just raise to the 1/2 power. You can use the radical tool, it's right there. So 9 minus t squared. And the second piece is just a clean t. And then we have, again, it's a radical, this time 1 minus t squared. And I know it's going to be happening because I tested the domain between -1 and 1. Oops. Then I hit enter. I hit enter, not shift. I hit enter. Oh, see what I did there? I confused myself. So it's the radical comma t comma, so it's the three components, but fortunately when I wrote it as the piecewise, it neglected the z component. So I was like, oh, something's off here. So when I hit enter, now it looks better, right? So now I look at my picture, I'll hit home, and you can see that it's only giving you a quarter of what you want. Now it's floating out in space, so it looks like it's incomplete, but that's what it should look like. You know, you can start zooming and everything like that, but this is what it ought to look like, right? We only focused on the positive radicals. We could have, because really when you think about it, you know, like if you start getting into probability also, you know, like a tree diagram, if you're flipping a coin 2 times, you can get heads, 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 tails, tails, heads, tails, tails. Well, it's the same thing with pluses and minuses. You can get plus, 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 minus, minus, plus, minus, minus. So if we were to do this all out by hand, we would have to then, after doing all this work, we would have to compute the negative radicals. So same stuff, but with negative radicals, then a mix with one positive, one negative, and vice versa, right? So this is definitely a little easier. This confirms, though, that we only have 1/4 of what we're looking for. So let me bring it back to the iPad. There we are. All right, so I know that my domain is going from -1 to 1. But ultimately, when all is said and done, I'm going to want to multiply this result by 4. All right. So what I'll do is I'll go into my little handy dandy program. I loosely use the word program. It's really just this script, but it's nothing too fancy. You know, so my f of x square root of 9 minus t squared. So I'm using x squared here. And g of x is just the x. And then 1 minus x squared. All right, so those are the 3 components to my vector. I get an area that's undefined, but that's, an arc length that's undefined, but that has to do with the fact that I have an a and b value that was from a different problem. All right, so I want this to be -1 to 1. I try to use the sliders, but my fat fingers don't always allow for it. So I'll just type this in as a 1. So I got 3.16 blah, 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 but I need 4 times that. So what I'll do is I'll just go back to the beginning on this one. We got everything the way we want. I'm just going to pop in a 4 there temporarily, because again, I want to save this line of commands for future use. So my S is going to be about 12.7 units. All right, but I want to take the chance that I'm going to forget. So I'm going to get rid of that 4 and then just kind of leave everything else the way it is. This kind of took off on me. All right, but you could see how this, you know, just taking the time to write a Desmos for just this one skill, it makes a big difference. And you know, like you may look at it and say, well, I'll just look online. I'm sure somebody else has already done it. Yeah, but they do it using their own vocabulary and their own nomenclature and their own terminology and symbology. We want to do it in a way that's particular to the way that we're doing it in this class. All right, so you know, take the time and get to know it. If you don't want to do that, then you know you're doing yourself a disservice. All right, so let me stop that recording.